talk about how hybrid treatment system can help us in building sustainability and resilience, and how the current systems are failing to match the emerging challenges of sustainability or climate related forcing, which makes us to develop systems which are resilient and cope up with the future challenges. So urban water management is basically where we are basically talking about all aspects of physical infrastructure such as sources, intakes, water treatment, transmission, distribution, water consumption, sewage conveyance, sewage treatment and disposal. Current approach is linear, where we take the water from the source, freshwater sources, maybe groundwater or surface water, and cities use this water and uh, partially treat it, not treat it, or in some cities, some initiatives of water reuse and recycling are happening. And a number of soft aspects of this urban water management are there, which may be the data monitoring protocols. A number of stakeholders are involved, such as planners, consultants, research organization, pollution control boards, public utilities, politicians, users, operators. So whole lot of stakeholders are involved, and which makes this particular problem both the uh, making the physical infrastructure correct and also applying the correct uh, strategies to bring all these stakeholders together is essential. So basically, effective culmination of relevant stakeholders in planning urban water infrastructure in a holistic manner will result in a sustainable and resilient urban water management. Because now in today's time, we need both of these aspects of sustainability, which encompasses the economic feasibility, technical feasibility, environmental feasibility, and also social aspects. That forms the sustainability basis. And then we also need systems which are resilient, which will cater to the emerging challenge posed by climate change. So if you see the current status of sewage generation and treatment in India, basically we have some states doing good on sewage treatment, but also their generation of sewage is very high. For example, in Maharashtra, you can see it is having uh, around 9,000 million liters per day sewage generation, but treatment is around about 7,000 million liters per day. Whereas some state, because of the topography and the current settings such as Kerala, where sewage generation is there, but treatment capacity is very minimal. Also in West Bengal, Tamil Nadu. So basically, these are the states which will be catching up with the sewage treatment systems. So, and if you see the in India, on an average, about 44% sewage treatment capacity, which is based on the recent data that was issued by Ministry of Environment, Forest and Climate Change. So basically, we have the challenge of sewage that is generated, and we have to create the treatment facilities. And now time has come to think of not as these are the treatment facilities, but as the new sources of water. So our treatment facility should be also providing some kind of water for secondary purposes, at least to start with. And then we have the industrial wastewater problem, which can be tackled separately or integrated manner in common effluent treatment plants. So overall, the sewage and industrial treatment is a challenge in India currently. We have been studying water is an important resource, but in current time, wastewater generated, which is a more important resource because of carbon, nitrogen, phosphorus involved available in this particular wastewater. So we'll see in this talk how these are very important. So these are the approaches for wastewater management. If you just talk about how we can move from that particular scenario of generated sewage to creating this facility, and we have different standards of, for example, historically we have been following 30 milligram per liter BOD standard, but recently Honorable National Green Tribunal has issued the order to bring down the discharge standard to 10 milligram per liter BOD standard. So now the challenge is we have to bring the older systems to this particular newer standard, and also the new sewage treatment facilities also meet this 10 milligram per liter BOD standard. One of the major approach that can be applied is the prevention conservation, where the reduction in water consumption will reduce the generated wastewater and sewage. So reduce consumption by awareness and efficient devices is one much more important. A lot of effort had not been placed on this particular aspect. Directly, the basically approach in all the missions and programs that we see is for treatment, and now people are talking about recycling, and then we'll go for recovery. So basically we will see how this hierarchy can be addressed, and treatment can be at the household or building level, or at the decentralized treatment schemes, or at the centralized treatment systems. And we'll see the problems in this different level of treatment systems. Number of treatment technologies, and in this talk I'm not going to introduce these particular technologies. You can refer to any other course or material. Physical, broadly these are classified as physicochemical or biological, where physical and chemical forces are applied, and filtration, reverse osmosis, these kind of treatment processes are there. Or biological and aerobic, anaerobic, which are USBs and other reactors are there. Then suspended growth, ASP, and SBR, extended aeration are there. Attached growth, trickling filter. So arena of technologies are there, and we can basically form a treatment change to uh, bring down the required amount of pollution level, BOD level, to by using this combination of these processes and operations. We have been doing this historically. We have seen sewage treatment is being done, but what's wrong with the current approach needs to be understood from a very holistic perspective of life cycle thinking. So basically, if you see, this particular is your city boundary or urban area, where we are basically households are consuming water, food, detergents and chemicals, and the generated wastewater is basically treated in the centralized treatment facility, where lot of times treatment plants are not functioning well. So effluent carries carbon, nitrogen, phosphorus, potash, and energy gets wasted. Also in the sewage sludge, a lot of these nutrients are there. And so the food, if you see the food is being basically produced from the agriculture, and from the agriculture we have basically nitrogen, phosphorus, and potash applied from industrial uh, uh, factories. So artificial fertilizers, for example, in India we have around 33 or 34 million tons of urea consumed per year, and which requires huge amount of energy for fix. So basically for producing these artificial fertilizers. So what we are doing is we are fixing nitrogen to produce this urea, and that is applied to agriculture. The agriculture is basically supplying this particular to food system, and food is getting consumed, and through our excreta, again the nitrogen and phosphorus is getting mixed in the water. What we are doing is again putting lot of energy for sewage treatment, and again taking out this nitrogen. So basically we are not completely optimize our uh, the urban metabolic system. Basically, we are consuming artificial fertilizers by fixing the nitrogens, and again we are taking out the nitrogens by, in both ways, in both times, putting lot of energy, and which is emitting huge amount of carbon dioxide. So you can see the carbon footprint of this entire system. So first we have to stop using nitrogen artificial fertilizers, and then we can create the new chain of fertilizers using this sewage sludge, and this nitrogen, phosphorus, and potash can be provided using this particular chain. A lot of our water resources are extracted from freshwater or dams or groundwater. This needs to be stopped or reduced, and new water can be created for secondary purposes. So a lot of these things can be done. So you can see we are basically, our conventional approach is avoiding extra effort and avoiding the life cycle thinking and the impacts. So basically we have to reduce the energy consumption for the sewage treatment, and we can create the energy from the sewage treatment. And this all possible from decentralized treatment system, and why I will explain in some time. So we have to work on consumer awareness as well to reduce the detergents and chemicals which are emerging contaminants and pollutants. So basically we have a lot of opportunities to close these loops and produce the carbon, nitrogen, phosphorus from available supply chains. So if you see the centralized and decentralized system, centralized is where everything is taken out of the city. For example, water is taken from the using the gravity is collected and taken out from the city boundary, and then it is treated. But what happens is this will be basically wasted or disposed into rivers or nearby ambient water body. But if you want to recycle, you have to again lay back the entire redistribution network. Whereas decentralized systems are, I'm not saying at the building or very small systems, but optimally scaled decentralized systems are very important to plan. And these can be where localize, not very, I'm not saying at the building level or household level, but at some community level, some neighborhood level systems will be very, very viable, where uh, instead of creating a huge system at one point, at one place, you can create such smaller systems, and redistribution network cost can be optimized. So this is the major difference between the centralized and decentralized treatment systems. So two small systems difficult to operate and govern. So hence I'm not saying decentralization means very local, very small systems, and those do not offer scale of economy. So highly centralized systems place challenges in recycling treated effluent and sludge, and there is no scale of economy beyond one point. And additionally requires deeper sewage networks for flat terrains. Okay, so basically we have the challenges on highly centralized systems and highly decentralized systems. So basically we have currently, if you see, consultants and contractors, politicians prefer this particular comfort zone of highly centralized system. So one DPR for one city, so that entire money can be taken out of the system in one go. So that is the comfort zone for many stakeholders. There are highly decentralized solutions promoted by some organizations where scale of economy is lost. So the ideal zone for recycling, reuse, and recovery is somewhere in between, and that scale needs to be identified for each of the cities separately by doing the detailed feasibility studies. So scale is more important than solution here to make the successful sewage treatment. So what I'm trying to say is we need a sustainability and resilience perspective for emerging urban water management challenges. Okay, so rational urban development can be achieved when both of these aspects of sustainability and resilience are taken into account. So basically, as I said, sustainability where the water infrastructure is affordable, acceptable, environmentally prudent, and relevant for a given location. Social aspects are taken care, and resilient where coping with the emergent hazard related to climate change. So even if the system is failing, it should reboot in a very faster manner. Okay, so that is the uh, urban water infrastructure which will lead to the rational urban development, and how that is possible through a hybrid treatment system I will discuss now. So we need both of these aspects, which basically we want a rational development where both resilience and sustainability is taken into account. And anything that is not matching this is not a, correct or a rational development of urban water systems. So this can be achieved using circular economy, and those of you are not aware of circular economy concept can refer to this particular report where the lot of conceptualization of circular economy is given. Basically, circular economy is where we want to maintain the resources in the same cycles. Whether so we have the technological cycles of materials. So basically materials are designed to recover, refresh or upgraded, and biological cycles where materials meant to be returned to the soil, composting or anaerobic digestion. So we are basically trying to close the loops of all the technical materials that we use and all the natural materials that we use. So conceptually, basically the term is circular economy because you need a lot of stakeholders to bring together to make this happen. So basically we need to do economic changes to bring the circularity of the resources. Hence the term circular economy is coined. In the context of circular economy for water, what we need to do is basically we have to monitor all the processes, what is going into the system, how we are designing, how we are consuming, and there are different requirements to be measured and actions involved. For example, for water cycle, uh, energy and chemicals consumed, effluent quality, carbon, nitrogen, phosphorus, biogas, and avoided emissions. These are need to be measured for designing the circular economy for water, and actions involved is what kind of business models, what kind of cascading is possible. And implementation can be at the macro level for entire city level, some sub zone, or for some small zone. Okay, so these are some examples of action that are involved for sewage treatment. So for example, extracting cascading value, process of which is called as process of extracting value at series of stages, beginning with the high value products to lower value products. For example, closed loop water systems can be full or partial and work at all scales. For example, city scale, Singapore is one example, industrial scale, building scale, or product scale. So you can apply this circular economy framework at different levels. So we have studied the circular economy for water in a very in-depth manner, where we classified the water in these particular 6 compartments, which is natural water, water treatment plant, urban area, wastewater treatment plant, industries, and agricultural land. And this is a system boundary where drinking water is basically extracted from the natural resources and supplied for different purposes or irrigation water. then the wastewater is generated from these all users, and then treated water or untreated water again goes back to natural environment. So currently what is happening is cities are using the water from the freshwater resources and dumping it without treatment or partially treated to the same resources, and downward cities or habitations are getting affected. So we need to enable this particular circular economy so that reduce, reuse, recycle, reclaim, recover and restore can be achieved. This can be possible when we first put a lot of effort on reducing the water consumption in industries, in agricultural areas, in housing areas. If we work on reduction, that is the first and prime most easy solution. Then reusing itself in the irrigation system, industrial system, cities, recycling, treating the water and again using it, reclaiming. Cities water can be reclaimed for the industries, or cities water can be reclaimed for agriculture. Restoring any additional treated water can be restored using managed aquifer recharge, and recovering the nitrogen, phosphorus and other nutrients is recovery. So we have to work towards developing these particular strategies, 6R strategies, and this is available. The entire detailed discussion and scientific work is available in this particular paper, which I will share the link in the YouTube description. So basically, whatever problem we are discussing, we have to think for production phase of the resources, from where the resources are coming from, how we are using the resources, and how we are disposing of. So end of life, use phase, reuse, remanufacture, closed loop recycle, and open loop recycle. So this is called life cycle thinking. We have to apply for water systems as well. And using life cycle thinking and circular economy, we have to take the decisions. So this particular 6R strategies needs to be coupled with 6 BIS principles of system thinking, value optimization, innovation, collaboration, stewardships, and transparency. So this our paper gives a very detailed idea about how this can be coupled to achieve the circular economy. Now, with this background of systemic thinking, what are the challenges in creating sewage infrastructure? Because this kind of thinking has not gone into the while developing our sewerage systems and treatment systems. So gap exists between the sewage generation and wastewater treatment, as I shown in the first slide. And we have mechanized treatment system, which most of the people working in water sector know, such as activity sludge process, membrane bioreactors, SBRs, which have a significant high energy consumption and very high, resulting in a very high operation and maintenance cost. Whereas there are class of natural treatment systems such as phytoremediation, constructed wetlands is one example, bioremediation, zoo remediation, and combined treatment. So basically, these are the treatment systems which are available options, which do not consume a lot of energy, but these are land-based treatment. So we have a trade-off between these technologies. One is mechanized treatment system, and other is natural treatment system. So basically, these trade-off needs to be understood, and then appropriate strategy needs to be developed. So our treatment goal should decide the treatment technology chain. For example, whether you want to SBR, active sludge process, MBR, USV, or constructed wetland, what is your end goal? Whether you want to use for high grade applications or whether you want to use for land irrigation. So what I see in a lot of public government tenders is no mention of the end use. Direct technology specified, one particular technology specified, which is not correct practice. Instead of specifying technology, what needs to be specified is the end use and the expected quality parameters and performance guarantee by the technology provider. Whichever technology they want to go for, they can go for. You can fix the per year operation maintenance cost, or you can fix the net present worth for 30 years, whatever quantitative criteria you want to use, but don't specify any particular technology, or specify all the technologies so that all the technology evaluation can be done. So basically, we have varied energy consumption, varied capex and operation maintenance cost, varied reliability and durability, and varied land requirement. So these are the number of criteria which can be used for the bidding process while evaluating the treatment systems. If you see the graph of operation and maintenance cost and land requirement, which are the primarily major criteria, because capital cost can be arranged by third-party funding agencies, such as many multilateral agencies are there, which will fund anyway the capital investment. The issue is after the capital expenditure happen, how the treatment system can sustain for next 30 years is the question not being discussed again and again. So we have to worry about operation maintenance than getting something implemented. Okay, so if you see the on x-axis, what I plotted is the BOD that is decreasing, outlet BOD. So it is a little bit a tricky graph, not a conventional graph. And on y-axis, I have plotted the operation and maintenance cost in rupees per meter cube. So if you see this MTS, which is this brown graph, it grows steadily, linearly, but as far as the more stringent standards to be met, the higher cost, higher energy is required. Hence, the operation maintenance cost shoot up very rapidly. Whereas natural treatment systems such as constructed wetland is plotted where energy is required very low, operation maintenance costs are typically stable. So basically, huge drastic difference is there between the operation and maintenance cost. Whereas if you see the land required for natural treatment systems is very high, whereas for the mechanized treatment system, land requirement is very low. So there is a clear trade-off between these two treatment systems, mechanized treatment systems and natural treatment systems. So at the BOD 3, if you see BOD 30 level, this graph becomes exponential at where we have to you have to shift from mechanized treatment system to the this particular natural treatment systems. So basically, which will reduce the operation maintenance cost and also reduce the land consumption, overall land consumption. So what I'm proposing is to use the hybrid treatment system approach where mechanized treatment system can be used for chunk of the pollution. So major of this pollution can be settled and with the very primary aeration maybe if required can be done and no sophisticated technology is needed. So basically you can use the simple settling tanks, take out the chunk of the pollution and then bring down the BOD to up to 30 to 40 milligram per liter and then shift to the natural treatment system using the available land area. Okay, so that is the hybrid treatment system approach, which is given in this particular paper. Complete scientific discussion is available. So what will happen if we use hybrid treatment system, which is given here, is the operation maintenance cost goes down drastically. So earlier it is for let's say 5 milligram per liter, it was 16 rupees per meter cube, can bring down to 6 to 8 rupees per meter cube. And this 5 milligram per liter BOD treated water can be used for variety of secondary applications such as toilet flushing, gardening, these kind of the applications are there. And land requirement also from natural treatment system goes down very almost half times the original land requirement. So, and there are different kinds of hybrid treatment system. You can use deep bed systems, constructed wetlands, which will further bring down the land requirement, or you can use shallow bed. So you can refer to the paper where a lot of details are given. So I have given here the numbers of hybrid treatment systems using the shallow bed or deep bed constructed wetlands. So if you use shallow bed constructed wetlands and if you use hybrid treatment system, you need around 3000 uh, meter square per MLD land for achieving the BOD level of 10. And if you want to achieve 5, then you need a little bit more area of around 4000 meter square per MLD. So this approach is more suitable for rural and peri-urban setting, both in centralized and decentralized manner where sufficient land is available. Okay, and this can be used in cities as well where STPs are located in the outskirts. So basically we have to take decision based on the location of the sewage treatment plant, or decentralized planning can be done for making this happen. If you see the life cycle cost analysis, because now if we are saying, okay, what about capital cost, that analysis also I have carried out. If you see in the capital cost, we consider civil works, electromechanical works and land requirement. Okay, so land requirement is also considered, and annual operation and maintenance costs such as labor, energy, chemicals and maintenance is also considered, and replacement cost after the 15 years, because after 15 years we have to replace the pumps, motor and electromechanical components. And we have used the as per IS standards present work method for analyzing different technologies. What result shows, and here the land cost I have assumed is rupees 1.6 crores uh, per acre. Okay, so basically this is the land cost that I have used. So you can see the land. This is the typically I have done the survey, and this is the average cost in, let's say, class one, or this typically 1 lakh population cities. So this is the 1.6 crores per acre cost, land cost is considered. Even if you consider such a high cost, the life cycle cost of 30 years of operation maintenance decides the which technology we chosen. And the analysis shows that in urban setting, even if you use the hybrid treatment system or natural treatment system, it is wise to use the land treatment system instead of any mechanized treatment system, because for the 30 years the municipality will end up paying energy bills every year, such a high cost that that money can be invested to purchase the land. Okay, and that will save us from also variety of other benefits, such as greening of the place, resilience will be improved, flooding will be reduced, because you are maintaining the land in the city. Okay, so it's a very drastic change in the thinking we have to do, that instead of investing in the mechanized treatment system, we have to invest into natural treatment system. Even if the buying of land is required, we have to buy the land. So life cycle cost analysis is very essential. So I'm showing you, even if the land cost is as high as rupees 1.6 crores per acre, the in even in urban settings, it is wise to use natural treatment systems or hybrid treatment systems. And definitely peri-urban and rural, no questions, we have to go for natural treatment system. So this analysis shows that in any setting, it is wise to invest in land and adopt natural treatment systems, which will help achieve both sustainability and resilience. So those who want to understand this better, the links for the papers and technical details are given. You can again redo this analysis and confirm for yourself. Again, I'm saying it is wise to invest in land for the treatment rather than going for a highly mechanized treatment system for Indian scenario. So this is the graph which shows the, again, the same results where capex is plotted for different settings. So what is the significance of hybrid treatment systems? Basically, National Green Tribunal has ordered that we have to bring down all the treatment systems to 10 milligram per liter level. So first, the older system has to be upgraded, which can be upgraded using constructed wetlands, and newer systems can be planned as hybrid treatment systems. So there is a demand for low cost and affordable wastewater treatment systems. Need to upgrade existing STPs, and decentralized infrastructure approach along with circular economy framework can be adopted for the wider implementation of hybrid treatment systems. So the additional benefits of hybrid treatment system is, if the proposed hybrid treatment system approach is implemented throughout India, total annual energy saving of about 200 gigawatt of energy can be achieved, and 350 gigawatt of energy can be used for the install in your feature. Okay. Additionally, this will save the carbon emissions and help in the climate change mitigation, around 0.45 million tons per year, considering the current India's electricity grid mix. And this hybrid treatment system can be easily implemented in around 400 cities, which is having population around 0.1 to 1 million. And for other bigger cities, HTS can be used by working with the planners and creating the land for the treatment, or buying land for the treatment and decentralized infrastructure approach. So overall, HTS approach creates the jobs for the local people, because now we are talking about natural treatment systems. Simple low skilled people can be used for the maintenance. There is opportunity to extract the resources such as fertilizers, bioplastics, huge amount of multiple supply chains of biomaterials can be created, and revenue generation for operation and maintenance can be is basically possible. So HTS adoption will help achieve both sustainability and resilience. That is the whole point I'm trying to make by giving this particular talk. I hope I made my point clear. So overall recommendation is, constructed wetlands are more suitable for Indian conditions, and constructed wetlands enable sustainable wastewater treatment, and this removes nutrients very effectively. And also, if emerging contaminants can be also tackled very easily using constructed wetlands. So in rural, peri-urban and or urban areas, first obtained for going for constructed wetlands or any other natural treatment systems such as ductweight systems or waste aeration ponds. And whenever land is not available or land cannot be purchased, then you can go for a hybrid treatment system approach. And there are large number of technology providers of constructed wetlands or any other natural treatment systems are available. And these natural treatment systems and constructed wetlands have reached maturity with a number of patents available. So open tendering for contractor selection, irrespective of technology, can be done. And standard constructive wetland design from handbooks can provide satisfactory performance. So you don't have need some patented technology or a very somebody is claiming some over claims. That is not required. Simple constructed wetland design based on manuals and textbooks can be adopted. So thanks for listening to the talk. These are my contact details, and I'm looking forward for collaboration to implement the HTS approach. And check the YouTube description where the links to download these papers if you want to verify what I'm saying, the numbers and the life cycle costing details. Please do so. So thanks for listening to the talk. Thank you.